Good afternoon, everyone. Welcome to the course Design of Reinforced Concrete Structures, Week 12 Problem Solving Session. This session is scheduled from 3 to 4 p.m. and in today's session, we will be dealing a problem related to uniformly loaded and simply supported rectangular slabs. Actually, these slabs are two-way slab section. So we will first look into some basic concepts and later on we will solve a design problem related to simply supported two-way slabs. So let's start. Uh, uniformly loaded simply supported two-way slabs. Consider a slab, rectangular slab like this, with Ly as longer dimension and Lx as smaller dimension, and such that its aspect ratios are such that Ly by Lx is less than 2. Okay, this is the basic definition for a slab to have two-way action, and it is simply supported. For simply supported, we have notations like this. You have to put crosses on all the four sides. Okay. This is our simply supported slab, supported on all the four sides. So let's divide it into small number of strips like this one. This is a strip along the mid surface like this one. 1, 2, 3, 4, 5, 6, 7, 8. Like this one. This is one strip along the mid surface, and we will take same strip along another direction, that's Lx direction. Let's draw from that side also. Just like this, and we will have another like this. Okay, this is clear, but we have to put them at the middle of the plan of the slab. Okay, so this is our CD strip, and this is our AB strip. Okay, these strips are along the center lines. Let me write that also, this one and this one. Strips along center lines. Okay, now if we see that one thing, we will analyze these strips individually. Okay, let's take this one strip first. This strip which is along the Ly direction. Okay, this one like this. I am making an exaggerated view of this one. This one. So it will be, if I see this strip, it will be simply like a simply supported beam like this one. Okay, with the UDL over it. UDL over it. Let us denote this UDL as WY. Okay, and it has a span of Ly. And its elastic curve is like this one. It will be having maximum deflection at the center, delta, and it will be given by delta will be equal to 5 upon 384 Wy Ly power 4 upon flexural rigidity Ei. Okay, and if we make a bending moment diagram for the same, bending moment diagram will be like this one, same like this one. Elastic curve, it will see like this one. Okay, it will have maximum ordinate at the center, and we will term this moment maximum moment my as, denote it as my, and it will be wy ly square upon 8. Okay, if we do the same thing for the strip which is oriented along lx direction, we will have again a simply supported slab like this one. Along this orientation, we will have an elastic curve like this one. You have to connect this everything with that slab one. Okay, I'm making them a little bit bigger to differentiate both of them. So it will be acted upon by wx. Okay, clear for to everyone. Will be wx here, and we will have a bending moment diagram same like that one. Maximum ordinate at the center, and let us denote that maximum moment as wx, mx, sorry, mx as wx lx square upon ei. These are the reactions which will be coming. It is dc strip, and the earlier one was ab strip. Okay, then we have a deflection of I'm sorry for the inconvenience. So we will have a moment of wx square ly square lx square divided upon ei, and we have a maximum deflection of maximum deflection of 5 by 384 wx lx power 4 upon ei. Okay, so now we are seeing the maximum deflection at the center of this rectangular slab in two orthogonal directions, but we can see that one beam is having one strip is having long span, and another is having short span. So in order to maintain the compatibility at the center of this rectangular beam, the deflections obtained in these two strips at the center point should be equal. So that delta along x direction will be equal to delta along y direction, so as to maintain the compatibility at the central point. So we will get, when we substitute these both deltas, we get 3 5 upon 384 wx lx power 4 upon ei. We have to equate it with 5 upon 384 wy ly power 4 upon ei. Okay. Oh, one more thing, we are assuming that the second moment of area, that's I, is same for both strips, that's along x direction and y direction. Beam is having isotropic moment of inertia. Actually depth is not varying, and so both strips are having same moment of second moment of area. So we will obtain a simple relation between wx and wy as wx is equal to wy iy upon ix का whole power 4. Okay. Also, in order to satisfy this force equilibrium, we will write wx will be equal to wy, and it will be equal to w. Okay, this one thing. So we will have from this equation, we will have we are having this equation and this equation. When we use these two equations, we will get wx individually as w times ly by lx. Okay, it will be if you solve it completely, it will be ly by lx ka whole power 4 upon 1 plus ly by lx ka whole power 4. Okay, if you denote this term ly by lx, that is aspect ratio, as r, if you denote it as r aspect ratio, you will get simply wx as w times r power 4 divided by 1 plus r power 4, and you have wy similarly as w times 1 by 1 plus r power 4. Okay, and we have also moments per unit width. I already wrote them. Let me write that again. Mx per unit width, because we are taking the strip per unit width of. Okay, mx will be wx lx square upon 8, same my per unit width wy ly square upon 8. Okay, when we substitute this equation, this is b equation and this is a equation, we substitute equation b in equation a, we get the expressions for moments mx as alpha x w lx का whole square and my as alpha y w times lx का whole square. Okay, where alpha x and alpha y are the moment coefficients. Okay, these alpha x and alpha y will be given as alpha x will be 1 upon 8 r power 4 1 plus r power 4. Okay, and alpha y will be equal to 1 upon 8 r square 1 plus r power 4. Okay, this one. We have these two moment coefficients. So uh, what we get by doing this formulation is that both the moments mx and my given by this equation c are in terms of span Lx. So if we have one short span effective span, we can get both the moments that will be acting, major moments acting on the slab, and we can design the reinforcement based on those moments coming. Okay. So we will solve a problem based on this formulation that we derived here. A small design problem. So what we have design problem 12 today. It's week 12 and we design problem 12. It's a design problem 12. It's saying that design a simply supported slab to cover a room with internal dimensions of 4 meter by 5 meter and 230 mm thick brick walls all around. All four sides are with brick walls. Assume a live load of 3 kN per meter square and a finished load of 1 kN per meter square. Okay, we are given that we have to use M20 concrete and Fe41 grade steel. Okay, also one thing is given that the slab corners are free to lift up and mild exposure conditions are to be assumed. Okay, so uh, in beams, if you apply that same formulation for effective span, okay, I'm not going to do the calculations here again because I have shown you in the case of beams how to calculate the effective span. Same is the case with the slabs, and also in the design of one-way slab I showed you how to calculate the effective span. So if you go back to those lectures and you calculate the effective span for this span. Okay, here short effective span where I have this like this one. This is 5,000. This is 4,000. Okay, so I will write it directly here. Okay, effective short span. Effective short span will be 4150. Okay, let me write also here details. That is plan is 4 cross 5 meter square. We have a wall 230 mm thick, and we have live load 3 kilonewton per meter square plus 1 kilonewton per meter square M20 Fe415. This is the whole thing we have been doing all the problems in these 12 weeks. Okay, this is nothing new to you people. Fe415. Okay, so we will assume a effective depth of thumb rule is assume an effective depth of effective span divided by, we will have it as 20 into 1.5, 138 mm. Okay, assume clear cover of 20 mm. Okay, because mild exposure conditions we are assuming, and for preliminary we are assuming 10 mm diameter bars. So clearing we get the overall thickness. So if you calculate the overall thickness D as effective depth 138 plus half the bar diameter, this one 20 plus 5 clear cover plus half the bar diameter, it will be 163 mm. Okay, so it has to be in the multiplies of 5, so provide 165 mm effective depth. Okay, so your effective depth along x and y directions dx will be 165 minus clear cover 20 minus 5 is equal to 140 mm. And dy, you have to, now this dy depth will be 140 minus, because like we are providing the reinforcement along one side like this one. If we are providing along one direction like this one, and then we are providing the orthogonal reinforcement over it, so this much of depth will get reduced like this one. If bars are provided like this along this direction, for this the effective depth is dx like this one. Now you have to provide along y direction like this one bar, you will provide a bar over this one, so it will be dx for this one, dx minus this one bar diameters, this one, this we have to subtract, so dy will be dx minus bar diameter, full bar diameter 10, dy will be equal to 140 minus 10 is equal to 130 mm. Okay, this is clear to everyone. So effective span we will calculate along both orthogonal directions as Lx, Ly, both are effective spans. Okay, make sure that effective span is equal to clear span, that is 4000 along Lx, plus effective depth 140. Okay, and along Y 5000 plus effective depth 130. Okay, so you get effective spans as along both orthogonal directions as 4140 and another 5130. Okay, mm. So you get a R value ratio, Lx effective by Ly effective, Lx by Ly, Ly by Lx, sorry, Ly by Lx effective comes out to be 1.239. Go through the calculations carefully. Okay, now loads on slabs, second point. Loads, self weight. Okay, first will be the self weight. Self weight at the rate of 25 kilonewton per meter cube into an effective span of 0.165 meter. Okay, because we have provided a overall depth of 165 mm, so that is 0.165 meter. Okay, this will be turned into a surface load of 4.13 kilonewton per meter square. Okay, it's easy to calculate. I have shown these calculations in detail in the design of one-way slab. So second is finishes. So finishes is already given as 1 kilonewton per meter square, and you are given as third point as live loads. Live load is already given as 3 kilonewton per meter square. Okay, summing up this everything and using a load factor of 1.5, you get an ultimate load of Wu is equal to 1.5 times, you get a value of here 8.13. Okay, when you calculate this everything, you get an ultimate factor load of 12.20 kilonewton per meter square. Okay, with this ultimate load you have to carry on the further analysis. So we will calculate the design moments from which we can get the reinforcement. Okay, so I already told you the corners are torsionally unrestrained, that is they are allowed to lift up, so we can use the methodology that I already explained to you. So moments will be given as the first design moment calculation. Design moments we will calculate from the moment coefficients and then this one. Okay, short span mux, it is alpha x times w u l x square. Okay, so you plug in the formula for alpha x that I already told, that is 1 by 8 r power 4 divided by 1 plus r power 4. Substitute the value of r as 1.239. I already calculated it here, 1.239. Okay, 1.239 substituting in this equation will give you alpha x quotient as 0.0878. Okay, and alpha y as 1 by 8 over square upon 1 plus r power 4. It will give you as 0.0571. Okay, so when you plug in mux will be equal to 0.0878 into wu is 12.20 into span alpha lx is 4.140 square. Remember, both the design moments are in terms of the short span. Okay, lx square. It comes out to be 18.36 kilonewton meter per meter. Okay, be consistent with the units. Since we were given the loading on the in terms of kilonewton per meter square, when we calculate the moment, we will get the moment per meter. Okay, design moment per unit width. MUY will be similarly as alpha y WU LX square. Okay, plugging in alpha y value as 0.0571 to 12.20 is the load and short span 4.140 square. It comes out to be 11.94 kilonewton meter per meter. So design moments MUX and MUY are these two things that you have to carry for the further calculations. Okay, the design of reinforcement. Coming to design of reinforcement. Design of reinforcement. Along the x direction, I will calculate the factor Rx. Okay, is same like in slabs and beams, everywhere we use it to do. Get the design moments. You either use design aids or the formulas directly. You can get the value of the PT. MUX by BD square. Okay, BDX square. Remember, putting the correct values along the correct direction. Okay, MUX 18.36. Moment was given in kilonewton meter per meter, so converting it into mm, it will be 10 to the power 6 unit conversion. Okay, B is 10 power 3 because it's, I remember it's per meter, 1 meter width. Okay, 140 square. Okay, when you get this, everything is in, I will, let me write the units as well so that you may not confuse yourselves. Okay, this will be Newton mm. Okay, Newton mm, and this will be mm cube into mm square. Okay, here it is. One more thing, vd, no, cube will not be there, it's only, mm. Okay, goes. Okay, it's Newton per square, it's megapascal. Okay, 0.939367. 0.9367 MP. Okay, this comes out to be, when we use a formula along longer span LRY, we will get MUY by BDY square. Okay, MUY is 11.94 in 10 power 6 Newton mm divided by width is 10 power 3 mm into 130 square, okay, square. This comes out to be 0.7065 megapascal. Okay, let me write a formula for the pt required. pt required upon 100 is equal ast required upon 100, sorry, ast required upon bd, it will be equal to fck upon twice fy, 1 minus under root of 1 minus factor 4.589 r upon fck. This is the basic formula. So I will plug in all the values for rx and ry, and fck fy are constant along both the directions. So I will get ast required, ast required along x, okay, I will get as 385 millimeter square per meter, and along y I am doing it simultaneously, yeah, please. Required along y is equal to 265.7 millimeter square per meter, okay. So spacing, if I assume 10 fibers, 10 mm diameter bars for lx, so spacing required s will be 1000 times a bar divided by ast, okay. Go back to your previous lectures, you will find this formula there, and I have derived it there also. Spacing will be equal to 1000 times area of bar for 10 mm diameter bar is 78, okay, 78 and a half, 78.5. ast along this direction is 385. Let me write simultaneously along other direction as well, okay. Here assume 10 5 bars, okay. So s squared here also will be 1000 times 78.5 upon 265.7, okay. When you calculate this thing, this comes out x sx 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 sy sy sx comes out to be 204 millimeter, sy comes out to be 295 millimeter, okay. So we will have to check maximum spacing for primary reinforcement, okay. Max spacing for primary reinforcement. What code says for this is it is either 3D or 300 mm. Now we have dx and dy, two orthogonal directions, so we will check for both of these. 3 times 140, 3 times 130, okay. Both 420 mm for short span, it is 390 mm for long span. Okay, so we will design our reinforcement like this. Provide 10 mm diameter bars at the rate of, so it is 420 maximum and we got 204, so reducing it to 200, okay. 200 center to center short span. Okay, we will provide 10 5 bars at the rate of, look, maximum is 390 and we got here 295, so reducing it to the lower of the two, we get as a multiply of 5 as 290. center to center. Okay, long span. If I calculate the AST provided here, AST provided is 392 millimeter square per meter. Okay, here AST provided is 270.7 millimeter square per meter. Okay, okay, so detailed diagram is like this. Okay, we had a plan like this, 4 by 5, this one. Okay, 4 by 5. Okay, it was having like this one. So we are given a slab panel like this, and it was having dimensions like this one, and it was 5,000 from this side. This was 5,000. Okay, this one 5,000 mm. This one was okay, this one, and this one was 4,000. Okay, 4,000 mm. We are having a walls of 230 mm thick on all four sides. I'm writing on only one side. Okay, these are uniform. 230, 230. Okay. So we have to provide the reinforcement like this one. I will make the two color codings like this one reinforcement like this, then bent, and then straight, alternate band bars. Okay, same another one will be like this up to this point. This will be a little bit bad there. Okay, this will be bent here. This one. So this is, these bars are 10 phi at the rate of 290 center to center. Okay, these are along LY direction. Another bar is coding this one, like this. These ones are I have provided as tan phi at the rate of 200 center to center. This is along y, this is along x, and y, this is along x. Don't confuse it with the coordinate system, it's just a direction, okay? And what else? This is the plan of floor. Go back to the lectures on design of one-way slabs. I have explained why we need to bend these bars and at what distance we need to bend. There I have explained it in detail. I will write only the dimensions at which I have bent them from the face of the wall, okay? 425 will be here, 525 will be here, okay? 525 mm will be here. Okay, the scheme I have already written. And let me draw quickly the section. If I cut it like this one, this was a section, okay? A section. If I cut the section like this one, this will be like this, this will be like this, continuous from this side, okay? This is this one, and it's supported on wall. This is like this, it is continuous like this one, okay? We have provided now we have provided the green, okay? Green along this direction, we have provided green like this, sorry, a little bit bold. We have provided green reinforcement center to center, and it bent it from the face of the wall like this one, bent it from the face of the wall like this, okay? And we have provided red reinforcement like this. Red is also 10 mm. We have provided it like this, 10 10 10 10 over it, sorry, these are blue 10 10 10 10 10, okay? This is 525. Band is made at 525 mm, and this is 10 phi at the rate 290 center to center, center to center. These red ones are 10 phi at the rate of 200 center to center along LX direction, and this is top bars. These are just for keeping this hook upwards. These alternate band bars, these are 8 phi bars, okay? And we have provided overall depth to this slab as 165 mm. 165, okay? Put this in mind. And 10 phi. Section A. What is this? This is section A. So this completes our design problem today. For today, we designed a two-way simply supported slab, which was covering an area of 4 meter cross 5 meter, and it was supported on all the four sides by 230 brick walls. Okay, so we calculated the reinforcement along both the orthogonal directions. This was all for today. Thank you so much for joining. Thank you. And one more thing, this was the last lecture from me, and from for the next week, two more lectures will be from other TAs as well. That's the end of this course. Thank you so much. Hope you have enjoyed.